Okay, so with this visualization we are done. And we will make an exercise, practical exercise. I just wanted to let you know. And we will start from a long-Gaussian and seasonal series. So we will have the opportunity together to apply in practice these transformations. In art, they are very simple. And now I think we are done with the category of the solution for dealing with data which don't meet our preliminary assumptions, Gaussianity and stationarity, because seasonality is a form of non-stationarity. So seasonality, I didn't tell you this before, it's, I said that it's different from variability. Seasonality, in fact, is a form of non-stationarity. And it's also called cyclostationarity sometimes, which in English probably is cycle stationarity. Yeah, cyclostationarity is Italian, it's a mix. I think it's cycle stationarity. But let's say that this is just a detail. Let's say that it's a form of non-stationarity. Okay, so we are done with this preliminary transformation to resolve the lack of the assumptions, the lack of satisfaction of the assumption. Now I want to talk very briefly about extension of this model, which I am rewriting. This model is the autoregressive model of order 1. I am rewriting it down because I already mentioned to you that in some cases the model could be not able to fit the data. Like epsilon could be still dependent, or there might be some other reasons, like the explained variance is too low, too low. And so, of course, there are some other solutions. This is not the only stochastic model that you can apply. So this is the AR1. First of all, let me say one thing that it's not so evident. This model, being linear, cannot generate intermittent series. Intermittent series means like the series of a river, which is dry during the summer. Intermittent means that there are zeros in the series, and let me say, by using an engineer's language, many zeros. Okay, not just one by chance, many zeros. Like you have a river whose hydrograph looks like this. If you make a hydrograph of qt over t, and t you have 365, let's suppose that you have 1 year, you have an hydrograph like this. 0, and then so you have dry summer, like torrents. Torrent, I think it exists in English, means typically a river who is dry for a long time in the dry season. In Italian it's clear, torrente means typically that it's dry during summer. So this model cannot simulate such a situation. This model cannot reproduce zeros. You see, epsilon is a random variable. You cannot impose zero values to epsilon. So you cannot reproduce a long sequence of zeros with this model. This is important to remember. So if you want to reproduce rainfall, this is not a good model. And then people devised other modifications. But let's say that autoregressive of order 1, it's a model for non-intermittent series. Now, what if what if the model doesn't fit the data? There is a first extension which...
Rob, I think I'm confused here. You gave a previous definition that it's generated intermittent series. Again, you're saying it generates non-intermittent series.
I said it's not good for intermittent series. It's not good. And therefore, the consequence, the logical consequence is it can be used only for non-intermittent. Okay. Now, a very straightforward extension is to extend the autoregressive order, not just autoregressive of order 1, but autoregressive of order p. And this is very straightforward. xt is equal to phi1 xt minus 1 plus phi2 xt minus 2 plus dot plus phi p x t minus p plus epsilon t. And you can include as many autoregressive components as you want. P is generic, and then it becomes A, R, P. Usually it is, you can use parentheses to identify the order, that P is the order. Okay. Then there is another extension, which is less straightforward, but still it's very easy to explain. Some people had a smart idea to extend this model. So, plus, by including dependence on past epsilons. So, plus. Let me use another symbol like theta for identifying a different class of parameters. So, theta 1, which multiplies epsilon t minus 1 plus theta q, which multiplies epsilon t minus q. And this is called moving average model. So you may ask me, what is the rationale behind this idea? What is the justification for expressing x depending on the autoregressive model plus a function of past errors? Okay, let me say that behind this idea there is an entire world of mathematical proofs which prove that this model, written in this way, this moving average model, is an excellent integration of the fitting capabilities of the autoregressive part. So, as I said, there are mathematical proofs proving that if you include this component here, which I call moving average model, you well integrate the fitting capabilities of this part. Still, the model is linear. And therefore, it's a good idea. So let me say that it's a good idea. Indeed, it's a good integration. But I don't want to go into the details and prove to you for what reason is this. And the resulting model is called AR of order P plus the moving average. So AR MA moving average of order Q. This is the resulting model, ARMA, PQ. Then let me say that there is another extension which I'm not introducing to you, but this further extension materializes by putting an I, which means integrated, between AR and MA. And then the orders are 3, because also there is an order called D of integration. I'm not going into details, I just want to introduce to you this ARIMA. And the reason why I want to introduce it to you is that this term is very known, much more than AR and much more than ARMA. In fact, in R, the software R, the function for simulating data from an autoregressive model is called, as I mentioned to you, arima.sim. So I wanted to explain to you what is the reasoning, what is the reason why they used this name for the function. Sim stands for simulation, but ARIMA stands for this autoregressing moving average integrated model. And you don't know what integrated means. I can anticipate that it's very simple, but I don't want to talk of that. The result is a very broad class of model. This ARIMA PDQ is the identifier of a very broad class of models. Linear. They are all linear. So basically, when you see this acronym, just assume that you know what is that, because you know the autoregressive, and it's enough. All the others, moving average, integrated, are just very slight modifications. Okay. Tomorrow we will make an exercise on this, so if you are attending, bring your PC as usual, and we will dedicate, I'm not finished now, I'm just, before I forget, I'm just reminding you to bring your PC tomorrow. Now, but I am done with the stochastic processes. I just want to make some final considerations, which are important, and also to introduce the next topic. And the final consideration, let me start from a question that you may ask me, which is, we know now two methods for generating synthetic river flows, let's say, synthetic variables. So which one should I use? This is the question. And should I use a rainfall runoff model if I want to generate river flows, or should I use a stochastic process? So which one? Okay, let's now concentrate on the differences between the two approaches. First of all, let me say that these are just two, there are many others. Like, for instance, if I want to generate an intermittent series, then I have to use another stochastic process. So you don't know everything. And there are other simulation techniques. For instance, a very used category is the resampling techniques. Resampling means that you get your data, and without fitting any model, you mix the data in order to get a replication. So you use the same number, but you mix them. Of course, mixing should be done in a way to preserve the features of the data. So there are other techniques. Let me concentrate on these two, and let's see the differences. First of all, rainfall runoff modeling needs rainfall input data. Stochastic modeling does not. You just need the observed data, river flows, to perform the simulation. You calibrate the model, you don't need the rainfall. So if your need is to generate synthetic river flows, with this approach you don't need the rainfall. Okay, this is the first difference. So basically, you should ask yourself, do I have the rainfall data to be used? Then I would say, if you have the rainfall data, probably rainfall runoff modeling is better because it allows you to use an information that it's available. Second, with the stochastic approach, you need river flow data. Do you have them, and are they extended? Because, you know, to calibrate a rainfall runoff model, you could use a very limited amount of river flow data. To calibrate a stochastic process, you need more data. And you may ask why this? Because, you know, with a rainfall runoff model, you have the information given by rainfall. With the stochastic process, you have only the information given by river flows. So if you have just, for instance, an event, a flood event, or let's say 2 months of hydrograph, if you use a rainfall runoff model, 2 months may be enough to calibrate the model. And then there is rainfall that gives to you the information on seasonality, how much is varying rainfall during the year, etc. If you use a stochastic process and you have just 2 months of data, where do you get the information for the other months? You don't have any means, so it's not enough to calibrate a stochastic process. For rainfall runoff modeling, you have the information given by rainfall. In this case, you don't. So let's say that if you have a very few river flow data, you have to use rainfall runoff modeling. You can't use stochastic processes. So basically, and also you could use both. So for instance, if you have to design a dam, you could generate the synthetic data by using both solutions if you have information enough. And then compare the results and maybe take the more conservative design. This is another possible solution. Basically, there is, even in this case, a holy rule. You have to use all the information available. So when you make a design experiment, in the presence of uncertainty, you have to maximize the use of the information. Because, you know, in the presence of uncertainty means that your predicting capabilities are reduced. So it's imperative to use all the available information. And then basing on the whole available information and basing on your knowledge of your problem and available tools, you decide what's better. By keeping into account that you have to explain to your client the reasons why you decided to use a given approach. Okay, that's good. And this is a complicated story, you know, to select the best approach for solving a design problem is not easy. And you need to be prepared and you need experience, where once again, experience does not mean long old age and doesn't mean that you have previous experience. Experience means that you know the problem and you know the tools. This is experience. Experience can be gained on the books. And experience must be gained by using your personal skills and intuition. It's not true that experience is just time. There are people who worked on some problems for 60 years, but they still don't have experience. There are people who worked just 1 year and they are very expert. So, you know, it's a matter of taking the right approach and giving a significant personal contribution. Okay, so now the next question is, let's assume that I generated my synthetic data. What should I do now? So we are starting from a water resources management problem. This is our starting point. We have to basically decipher water resources availability. So now we are at a point where we can generate river flows, or groundwater levels, or whatever. And let's suppose for now that we are interested in river flows, because I mentioned to you that the easiest way to get water is to get the water from the river. And it's easy because it's available water, you see where it is, it can be observed, and also it's already available, you don't need to pump it. If you take the water underground, you need to pump it, and it's costly. From the river, it's very easy. Of course, today the rivers, there is the problem that they are polluted. But in the past, they were not. And therefore, it was very easy for people to get the water there. So let's suppose now that our problem is to get water from the river. And how to decipher, the next question is how to decipher water resources availability in a convenient way if we are dealing with the river flows. And there is an important tool, which I think you already know, but I'm not sure, because when dealing with international backgrounds, it's they are very different, so I'm not sure. But this tool, which is a graphical tool, it's called flow duration curve. So now I am introducing the flow duration curve, which is a very important support for solving water resources management problems when dealing with river flows. So the flow duration curve. This is not the only tool that is available. I anticipated to you that our basic tool is the water balance, okay? But in order to quickly decipher river flow availability, the flow duration curve, it's a great support. It's a graphical tool. Graphical tools are very important and are much used in engineering in general, and especially in hydrology. I can speak for hydrology, they are much used. Because the graphical tool has the advantage of being transparent and clear. They were introduced, graphical tools, in the past for a different reason. They were introduced because the computing capabilities were much more reduced with respect to today. And therefore they had to use graphical tools because they couldn't use numerical integration. But the graphical tool has also the nice advantage of being very transparent. So if you can draw a graph when you speak with your clients, with the people, it's always better. And the graphical tools are now a bit substituted by object-oriented programming. So instead of using R, which is difficult to explain to people, because if you run R in front of a public assembly, people can't follow you. You may use a different software that is object-oriented. Object-oriented means that you display over the screen the various components of your water resource system by using objects. Like you can display in the screen something like, instead of displaying the R code, you're displaying something like, here I have the dam, and then here is the river, here I have the pumping station, and here I have a reservoir, a compensation reservoir, and here is the city. And then you display over the screen an equation like if this is Q3 and this is W, then here you have an equation which is plugged in here, which says like Q3 is equal to K times W. So you display the equations over the objects. This is object-oriented programming. And many decision support systems are devised in this way. An alternative is the R code, any code, but the code is not legible, it's not transparent. Object-oriented programming is transparent. And graphical tools are being, in some cases, replaced by object-oriented programming. But now let me introduce the flow duration curve, because it's a graphical tool that in water resources management is still much used. And the flow duration curve is a graph. A graph in 2 dimensions where you have the river flow in the ordinates. Not QT, it's not a good idea. Let me just write Q. And what is Q? Q is the river flow in a given location. Okay? Of course, when it's measured, it depends on time. But when you put the data together, you just have observation of river flow. You can put the data together and indicate them just with the symbol Q. And then in the abscissa, there is what is called the duration. And let me assume that we are dealing with daily data, but the definition can be extended to whatever time step. But let me assume that we have daily data. So basically, the flow duration curve, I am repeating what I'm saying, so don't be concerned by writing down while I'm speaking, I'm repeating. The flow duration curve shows in correspondence of any value of the river flow the average number of days during the year in which the river flow, the given river flow, is reached or overpassed. So let me state again. For a given river flow, the flow duration curve is associating the average number of days during the year. So for a given river flow, the flow duration curve gives the average number of days during the year in which it is reached or greater than that. Gives the average number of days during the year in which the given river flow is reached or overpassed, or greater, let's overpassed. So, let me start from Q max. And, or let me say, Q max is not a good example. Q star. What is the average number of days during the year in which Q star is reached or overpassed? Let's say that it's 1. This means that Q star is reached 1 day in a year or overpassed on average. Let me take now a lower value, QW star. What is the average number? So basically I'm starting from here. For Q star, the average number of days is 1. Q double star is lower. What is the average number of days again in which QW double star is reached or overpassed? It will be greater because it's lower, the river flow, so I'm expecting something like here. The flow duration curve may have this shape. It is extended from 1 to 365. It could be like this. It could also be like this. You may reach the abscissa for a duration lower than 365 if the river is intermittent. The shape can be very different. But you understand that it's very important because your client may ask you, I need a river flow that is equal to Q prime. So I need 10 cubic meters per second to feed my water supply system. how many days into the year I have this water available. Then you take the flow duration curve, you go here and you get your estimate. And you may tell to your client, look, the average number of days in which you have this water resource available is this star. For the remaining days, you have a lower river flow available. So the flow duration curve is very useful. And of course, this is the average number of days during the year, which means that you need many years to compute the flow duration curve in a reliable way. The flow duration curve can be computed also for 1 year only. You can do that. But then it refers to just that here. So it's not the average number of days during the year in which a given river flow is reached or overpassed. It's the number of days in that year in which the river flow was reached or overpassed. So you can refer to 1 year only. But then it doesn't give an average indication. It's just give an indication for that year. If you want a reliable estimation of the flow duration curve, you need many years. And to emphasize the importance of the flow duration curve, I may provide you an example. When we design an hydropower plant, experience tells us that the design flow, the optimal design flow for the hydropower plant is corresponding to the flow with duration of 60 days. This is a rule of thumb. So this is our first guess. If a client comes and says, look, I want to build an hydropower plant on this river, I have the authorization to do that, what is the optimal design flow for my hydropower generator? I would say, okay, give me the flow duration curve, take the river flow with duration of 60 days. This is your optimal design. This is a rule of thumb. Of course, when you make the final design of the plant, you need to make some more refined verifications because it depends on the cost of the energy, the cost of selling, let's say, yeah, the selling cost of the energy. It depends on the cost of the dam, the cost that is needed for bringing the water to the plants. Many variables are interfering, but a rule of thumb is duration of 60 days in the year. And you may ask me, why don't design the hydropower plant for the maximum flow? Because it's more costly. So if you design for the maximum flow, you have that flow for just 1 day in the year. So which means that on average, your hydropower plant works at full regime 1 day only in the year. So it's more costly and you don't use it fully. So you have to reach a compromise between the amount of resource that you are using, you are exploiting, and the cost of the plant. Of course, if you reduce the design flow, you reduce the cost of the plant. Okay, so next question is how to estimate this flow duration curve. I have the data now, I have the synthetic data. How can I estimate it? And it is very straightforward, but still, I think it needs some careful thinking because we have two methods that we may use. So let's suppose that we have whatever years of data, because given that we generated the data, we may have 1,000 years of data. No limits, no limitation to the amount of data because we generated them. But in order to make it simple, let me assume that we have 10 years of data. So let me say that capital M is 10. How to estimate? My question is how to estimate the flow duration curve. Okay. First of all, let me draw the axis. And for the sake of generality, let me start now from 0. The duration from 0 for the sake of generality. No problem, here I started from 1, but I can depict the same graph even if I start from 0, just to be general. And then here I have 365, because I'm still assuming that I have daily data. And then let me put D here and Q here. Now, let's suppose that we have 10 years of data. Let me make a first consideration, a first conclusion. I already made the premise, and I made it on purpose, that you could draw a flow duration curve for the duration of 1 year. And let's do that. If we have 10 years of data, let's focus on the first one, and let me draw the flow duration curve for the first year. And then let me say that I am, for instance, in Excel, working in Excel, doesn't matter, it can be R, but in Excel it's easier because I can draw on the blackboard how it looks. So let me put the Q for the first year, and this Q go from 1 to 365. I have 365 numbers, and let me write down here an index from 1 to 365, and let me put this data, this Q, in descending order or decreasing. Let me say decreasing. Descending, I'm not sure it's correct. Okay, so just to summarize the situation, I have here numbers from 1 to 365, and I have the river flow